Hello, in this session we are going to focus on the inverse normal distribution. The inverse normal distribution has to do with destandardization. That means the reverse process of standardization, whereby we try to find the Z value or the Z score that corresponds to a particular given probability. We look at this diagram of the standard normal distribution. There is a Z score A whose area to the left on the standard normal curve has been shaded, and that area corresponds to the probability value P. A situation might arise where we know P and then we want to find that Z score A that gave the P, or we might want to find instead the observation of that Z score. So whatever the case, it would require that we walk backwards by first using the inverse normal distribution function in order to arrive the Z score that gave that P. Then phi of A, because it is the area to the left of A that is shaded, that phi of A corresponds to the probability P that has been given. To have that Z score A that gave that probability P, I would need to use the inverse phi function. So I would take inverse phi of both sides of the equation so that I now get A to be equal to phi inverse of P. That would give me the relationship between A and P, where A has been made the subject this time. Now, before we proceed, it would be very important for you to know that problems that involve destandardization, that means finding the Z score when the probability value has been given, are usually very challenging. So you make sure you follow up carefully in order to see the tricks and the tips that are involved in such calculations. Let us take the case where we have phi of A equals 0.9406. To have the Z score A that led to that probability value, I will take phi inverse of both sides so that I get A equals phi inverse of 0.9406. And from there now I can go to the table. So on the table I would locate 0.9406. So 0.9406 is located here. So what I would do now is I would take from that value horizontally to the extreme left, where I will read the Z score and its first decimal point as 1.5, and then when I go up vertically, I will read the second decimal place as 6. So my Z score that corresponds to 0.9406 is 1.56. In the majority of the cases, the exact probability value would not be found in the body of the table, so that you'll be forced to use the add section in order to get the exact Z score for that probability value. So we have this case phi of K equals 0.6198, so that K should be equal to phi inverse of 0.6198. From here now I go to the body of the table and I have 0.6179, and the next one is instead 0.6217. So the closest value to my target value of 0.6198 is 0.6179. So I had to look for the value. Once your target value is not on the table, you look for the value closest to that target value but less. The target is always to look for the one that is closest but less if the target probability value is not in the main body of the table. So once I've had that value that is less than the target value but closest to it, I will read the Z score that gives it, and the Z score would be 0.3 for the first decimal place and then 0 for the second decimal place. So I have 0.30, and the next thing I will have to do now is to find the difference between the target probability value and this value that I've had the Z score of 0.30. So I take 0.6198, the probability value that I was seeking to find the Z score, and I subtract the one that is closest to it but less, which I've had as 0.6179, and upon subtraction I get 0.0019. So that is the difference between my target probability value and the one which is closest to it but less. So that difference, which corresponds simply to the whole number 19, I'll go to the add section in the same row that I have read the value that is closest to my target probability value, and from there now I will look for the value 19 in the main body of that far end where the add section is. That 19 now, the difference of 19 corresponds to the digit 5, which now becomes my third digit in the Z score, and so my Z score is supposed to be K equals 0.305. So this is the z-score that gave the probability value of 0.6198. In the case where we instead have the probability that the z-score is either less than or greater than, or even lying in an interval, then we have to be very careful. It is either the unknown z-score would be negative or positive. It depends on the direction of the inequality sign as well as the value of p. So in this section, I'm going to show you how you can be able to recognize whether your z-score will be positive or negative. This is where the questions are usually tricky. If you take a z-score and use the wrong sign for it, you would get a wrong calculation. So take note of this. We want to see the cases where the z-score will be positive. This is a standard normal distribution curve that will help us to understand when to judge that a z-score we are seeking to find is a positive value. If a z-score is to the right of 0, it means that it will be positive. So this a would be positive. When the probability value is given now, how do you recognize the positivity of that a? So the area to the left of a, p of z less than a, is equal to a certain p, and that area to the left is greater than 0.5. From a down to the lower limit of the curve, the area is already more than 0.5. So when p is greater than 0.5, so where you would have the less than inequality and the value of p is greater than 0.5, you would know that you are dealing with a positive z value. So in this case now, I would have to say phi of a equals p, since that area lies directly to the left of a, and from there a would simply be phi inverse of p. If instead I have the probability p prime, which is the one on the right, and I need to find the z-score in this case, the fact that a would be positive, this other probability p prime should be smaller than 0.5. You can see that that value is smaller than 0.5. It is a very small probability. So if I have the greater than inequality and my probability value is less than 0.5, it means that that z-score would be a positive value. And so we can write that p of z greater than a is simply 1 minus phi of a, and that should be equal to p prime, so that phi of a would be 1 minus p prime, and then we have that a, which is positive, should be phi inverse of 1 minus p prime. And that is how you get the positive z-score in this situation. Now, in the case of negative z-scores, you would have to be very careful. Usually a z-score that is negative would lie to the left. Let us call it a without the sign, but that a has to come out negative. So if a is negative as it lies to the left of 0, there are two situations. If the probability to the left of a, call it p, is less than 0.5, then that a has to be negative. So it means that p of z less than a is equal to a certain p, the probability value, and you notice that p is less than 0.5. Usually by sketching the graph, you should be able to predict whatever the case may be. The way the probability value is given, you would be able to know directly, but the sketch would clearly make it. So always make the sketch in order to judge whether the area is less than 0.5 or greater than 0.5. So when the area covers from the extreme end and crosses the line of symmetry, we judge that it is already more than 0.5, because from one extreme to the line of symmetry is 0.5. And it means that if I indicate the negative of that a to the right, then it corresponds to positive a, because a being negative to the left and it has not been indicated, it means that the positive value of a is the negative of that value, which now would appear on the right. And again, by symmetry, we would have that p of z greater than negative a is equal to that probability value p by symmetry. So this is still p. And from there, normally p of z greater than negative a, which is actually positive because a is negative, so negative of negative gives positive. Probability that z is greater than a certain value, which is supposed to be positive, boils down to 1 minus phi of negative a equals p. And so making phi of negative a the subject, we have 1 minus p. so that negative a would be equal to phi inverse of 1 minus p, and so a would always be negative phi inverse of 1 minus p. Let's take an example. In that case, my k has to be negative because the area to the left of k is so small, less than 0.5. So I will now have that the area instead to the right of negative k should correspond to that 0.3421. And once I've written this statement, I can just skip directly into the format that we have there. So k should be the negative of phi inverse of 1 minus 0.3421, 0.6579, which you can now go to your tables and you read the value from there. I already said that when a is negative, it is either the area to the left is less than 0.5 or the area to the right is greater than 0.5. So another situation where a would still be negative is where we have p of z greater than a equals a certain value p, and p is greater than 0.5. This still depicts the situation where the z-score a that we are seeking to find is negative. So in this case, the area to the right of a, p of z greater than a, which is negative, corresponds to p of z less than a, which is positive. So to make a that is negative positive, I have to negate it. P of z less than negative a is simply phi of negative a, which should actually correspond to p of z greater than a, which is negative. So, and that value is simply p. It means that negative a would be phi inverse of p, so that a would be negative phi inverse of p. So this is the turnaround in the case where z is negative because the area to the right is greater than 0.5. Again, let us take an example. Suppose I had p of z greater than t being equal to 0.7523. In this case, the area to the right of t, the unknown z-score, is greater than 0.5, so the t should be negative. If t is negative, then the area to the right of t corresponds to the area to the left of positive t, and positive t is obtained by negating the t because the t has to be negative already. So we can say that p of less than negative t, which actually stands for positive t because t is already negative, if you negate an already negative value, it becomes positive. That value corresponds to 0.7523, so that this, which is now phi of negative t, should be equal to 0.7523, and so negative t would be phi inverse of 0.7523, so that t becomes negative phi inverse of 0.7523. And from there you can now go to the tables and follow the procedure which we outlined before to get your z-score, which when negated gives the value of t required. Okay, we proceed now to see concrete examination type questions so that we actually develop our skills on what we have just learned. The first question we have here says x follows normal distribution with parameters 100 and sigma squared. So 100 is the mean of the distribution, and p of x less than 106 equals 0.8849. Find the value of the standard deviation sigma. We are dealing with the raw data value x, which has not yet been standardized. So in that case, we would start by standardizing the x value. So p of x less than 106 corresponds to p of z less than 106 minus the mean of the distribution, which is 100, divided by sigma, the standard deviation that we are seeking to find. And we are told that this probability is 0.8849. So p of z less than 106 minus 100 all over sigma is the area to the left of z, and it corresponds to phi. And since the area to the left is greater than 0.5, so we have phi 106 minus 100 will give 6 all over sigma equals 0.8849. So that 6 all over sigma should be equal to phi inverse of 0.8849. So to read phi inverse of 0.8849, I would look in the body of the table. So this is 0.8849. It is found on the table, and it corresponds to the z-score of 1.2 and 0 for the second decimal place. We then have that 6 all over sigma equal to 1.20, so that 1.2 sigma equals 6, and sigma then will be equal to 6 all over 1.2. So we have that sigma equals 5. In the next question, we have this question from Further Mathematics of GCE June 2016. It says the masses of grapes from a particular orchard are normally distributed with mean mu and variance sigma squared. Given that 5% of the grapes have masses greater than 80 grams and 10% have masses less than 20 grams, find the values of mu and sigma, giving your answer correct to one decimal place. So x is the random variable, the mass of grapes, which follows the normal distribution with parameters mu and sigma squared. In the first case, we have given that 5% of the grapes have masses greater than 80 grams. So we are talking of P of x greater than 80 being equal to 5%, which corresponds to 0.05. We have P of z. So we begin the standardization is greater than the x value minus the mean of the distribution divided by the standard deviation. That should be equal to 0.05. So 0.05 is less than 0.5. So here we simply write that 80 minus mu, the positive z-score, is equal to phi inverse of 1 minus that small value of the probability, which is 0.05. And from there we have that 80 minus mu all over sigma is equal to phi inverse of 0.95, which we can then read the value from tables. In the body of the table, I would check where 0.95 is. I instead have 0.9505. So that value and the one to the left is already below 0.95. So I'm going to take this value first, which is very close to 0.95 and less than it. So we have on the extreme left 1.6, and at the top of that score we have 4, so 1.64. What we need to do now is to get the difference between our target, which was 0.95. We subtract the one we are just from getting the z-score just to 2 decimal places, which is 0.9495, and the difference will help us to get to the third decimal place. This gives 0.0005. So the probability difference is 5. So I'll go to the add section along the same row where I've gotten the probability value that gave the z-score just to 2 decimal places, and follow horizontally where I would see a probability difference of 5, and this is it. I go up to the top of the table and read the digit that corresponds to that difference of 5. That digit becomes the third decimal place of my z-score, so 5. So we have that 80 minus mu should be equal to 1.645 sigma when you cross multiply. Mu plus 1.645 sigma should be equal to 80, and that gives equation 1. Since we have 2 unknowns, we have to get another equation and then solve simultaneously. The other part of the question says 10% have masses less than 20 grams. So we have that P of x less than 20 equals 10%, which is equal to 0.1 when you divide 10 by 100. So again, we standardize P of z less than the x-score minus the mean all over the standard deviation should give 0.1. 0.1 being less than 0.5, it means that our z-score here has to be negative. So but we know that phi of 20 minus mu all over sigma should be equal to 0.1. From here, we can turn around by now saying that 20 minus mu all over sigma should be equal to the negative of phi inverse of 1 minus 0.1 according to the shortcuts that we established earlier. This will be the negative of phi inverse of 0.9. So it gives negative a z value corresponding to 0.9, which I can now read from the tables. I would go again to the table and check where the probability of 0.9 or a value closest to it but less than is found, and there is 0.8997. so we have this value which is closest to 0.9 but less than it, and it corresponds to a z value of 1.28. so I have to put the negative of 1.28, and then now I get the difference between 0.9 and 0.8997, which gives 0.0003. So there is a difference in probability values of 3. I would go along that row and check where the probability difference of 3 is. So on that same line, I have 2 and 4, but there is no 3. I have the option of taking the difference of 2 or the difference of 4. So if I take the lowest value, which is 2, it corresponds to the third digit of 1, which I can now put here, and my z-score would be negative 1.281. And from there I have that 20 minus mu all over sigma should be equal to negative 1.281. Cross multiplying and rearranging, we have mu minus 1.281 sigma equals 20, and that gives equation 2. Remember, we are seeking to solve for mu and sigma, and that will be done simultaneously. We already have 2 equations. So if we take 1 minus 2, mu minus mu, which is 0, 1.645 sigma minus 1.281, that will give us 2.926 sigma, being equal to 80 minus 20, which is 60. So that sigma would be equal to 60 all over 2.926, which gives 20.5 grams to 1 decimal place as the question specified. So the standard deviation sigma equals 20.5 grams. Now substituting the exact value of this sigma in equation 1, we have that mu equals 80 minus 1.645 into the value of sigma, and we're going to take the exact value for accuracy reasons. So 60 all over 2.926. This will give 80 minus 33.732, which gives 46.3 grams to 1 decimal place. So that is the value of mu. The last question, the question says the lengths of rods from a certain factory are normally distributed with mean mu cm and standard deviation 6 cm. It is known that 4.78% of the rods have lengths greater than 82 cm. Find the nearest integer. 1, the mean mu. 2, the range alpha, symmetrical about the mean, within which 75% of the rods lie. Find also, to 4 decimal places, the probability that a rod chosen at random has a length between 62 cm and 72 cm. This was a past question of Further Mathematics Paper 3 of the Cameroon GCE June 2020. The lengths of the rods should follow the normal distribution, with the parameters being mu and 6 squared, since the standard deviation is 6. So in the first part of the question, we are told that it is known that 4.78% of the rods have lengths greater than 82 cm. Now to find the mean, we have to use that condition. So P of x greater than 82 equals 4.78%, and that gives 0.0478 when you divide 4.78% by 100. And we proceed to standardize, whereby we now have P of z greater than 82 minus the mean mu, that we are seeking to find divided by the standard deviation 6 should be equal to 0.0478. Now, the fact that the area to the right of our z value is less than 0.5 means the z value is positive. In our shortcuts that we saw, if you had the probability that p of z is greater than a particular unknown score and the probability value is less than 0.5, it means that your z score that you are looking for, which is 82 minus mu all over 6, should just be phi inverse of 1 minus the probability value. So we have 1 minus 0.0478, which would give phi inverse of 0.9522. So in the body of the table, I have a value of 0.9525, which is already greater than 0.9522. The value to the left is 0.9515, which is less than 0.9522, smaller than it but very close. So I would first consider 0.9515, and it corresponds to a z value of 1.66. So we have 1.66, and then we find the difference, 0.9522 minus 0.9515, which gives 0.0007. So a probability value of 7. We have to locate it horizontally at the add section, and it is found here. So the value at the top that corresponds to that difference of 7 is 7 itself. So we have the third decimal place of our z score as 7. So 82 minus mu all over 6 should be equal to 1.667, so that we have mu equals 82 minus 6 into 1.667, which gives 71.998. Since we were told to find mu to the nearest integer, we have that mu equals 72 when you round 71.998 to the nearest integer. And we're dealing with lengths of rods in centimeters, so mu is approximately 72 centimeters to the nearest integer. Now, in the second part of the question, we are asked to find a range alpha which is symmetrical about the mean, within which 75% of the lengths of the rod lie. So part 2 of the question, let that symmetrical range alpha be such that the observation x1 less than or equal to x less than or equal to x2, so that the corresponding z scores should be z1 less than z less than z2 respectively. So in that case, we have to draw the standard normal curve in order to visualize what is happening. We have the line of symmetry which corresponds to the mean of the z variable 0, and then that range is symmetrical about 0 in such a way that my z1 will be to the left and my z2 would be to the right. So I have to start by finding the corresponding z values before I can get the corresponding x1 and x2, which gives the range required. Now, we have been told that that range should be symmetrical about the mean, so that this area corresponds to 0.75 or 75%. So we are going to be interested in the cutoff values which represent the vertical lines z1 and z2. So if I have the middle shaded area there corresponding to 0.75%, and because the whole curve is symmetrical, it means that when you subtract 0.75 from 1, you get the remaining area as 0.25. So that area will be divided equally between these other two regions which are left, and those two regions are also identical due to the fact that there is symmetry in the diagram. So this area would be half of 0.25, which is 0.125, and the other area equally is 0.125. So as I said, I'm interested in the boundary values z1 and z2. If I have them, I can then work backwards to get the boundaries of the range that we're looking for. So we have to note that z1 and z2 lie at equal distances from 0, which is the line of symmetry. So while z2 is positive, z1 is the same value in magnitude but negative. So it suffices to just get one of the values, and it is easy to get z2 by considering the area to the left of it. P of Z lying to the left of Z2 would correspond to the area 0.125 plus the shaded area, which is 0.75. So we have 0.75 plus 0.125, which gives 0.875. Since it is the area to the left of Z2, we have that phi of Z2 should be equal to 0.875, and Z2 would then be phi inverse of 0.875. Now in the body of the table we do not have 0.875, but we have a value very close to it, which is 0.8749. It corresponds to a z-score of 1.15. So I write 1.15 as the z-score. Then I find the difference between 0.875 and 0.8749. That gives 0.0001, giving a probability difference of 1. In the body of the table, we don't have 1, we have 2 and then 4. So we take the one closest to 1, which is 2. And going up at the top, we can read the third decimal place of our z-score as 1. So Z2 equals 1.151, and it is positive since the area to the left of Z2 was bigger than 0.5. Z2 corresponds to the observation x2. So that Z2 would have come from the standardized value x2 minus the mean, and the mean value of the distribution was calculated as 72. So we have 72 all over the standard deviation, which is 6, should be equal to 1.151. X2 can be made the subject, which should be 72 plus 6 into 1.151, which upon calculation gives 78.906, so that X2 becomes 79 centimeters to the nearest integer as the question specified. Now in the case of Z1, it lies the same distance to the left of 0, so it is the negative of the Z2 that we had, so negative 1.151, and we are seeking to find its observation x1, which is the lower boundary of our range. X1 minus the mean 72 all over the standard deviation 6, which corresponds to negative 1.151, so that upon making x1 the subject, we have that x1 equals 72 plus 6 into negative 1.51, which upon simplification gives 65.094. Since we want the value to the nearest integer, x1 should then be 65 centimeters. The lower bound x1 equals 65 centimeters and the upper bound x2 equals 79 centimeters. So we can conclude that the range alpha that we are asked to find is in such a way that 65 is less than x and x in turn is less than 79. Now the third part of the question says the probability that a rod chosen at random has a length between 62 centimeters and 72 centimeters. So this one is easy to find. We already have the mean as 72 and the standard deviation is given as 6. So it is left as exercise for you to do. This video is the third in the series that I have made concerning the normal distribution. You look at the description of this video below and you would see the links to the other videos, which are very important for you to complete your understanding of the normal distribution. Then for those who are new to the channel, please consider subscribing and activating the notification bell so that anytime we post a new video, you would get the alert and then watch.